All right. So back to this discussion. We started by looking at the equation for the net force, Newton's second law, that says that it should be equal to the mass times the acceleration. And then we wonder what the acceleration was in the case when we're talking about a system that has different parts, and maybe the different parts of the system are not moving with the same acceleration, right? Remember that in general you can talk about a system as a collection of objects, right? Whether they're moving together or not, you can still call it a system, and you can apply Newton's second law for any kind of system that you might have. So the picture that I wanted to put in your mind was this tennis balls attached to each other by springs, and you make a bigger ball made of tennis balls that are attached to each other by springs. So you kind of move this thing around and it just flops like this, right? And all the tennis balls are moving in different directions. They're attached to each other, but they have a lot of play, right? And then you swing this thing in the air. And then I ask you, well, if we're applying Newton's second law to that object, to that very floppy object, what would be the mass of the system? What would be the acceleration that we're dealing with when we use Newton's second law, right? So the answer is that the mass of the system will be the mass of all of the balls and the springs in the system, right? And the acceleration that we're talking about is the acceleration of the center of mass of that floppy ball, right? The center of mass. So how do we define the center of mass? The position of the center of mass is given by this divided by the total mass of the system. Okay? That would be in the x direction. If you want the location in the y-axis of the center of mass, then you would you would use the same equation, except that now instead of looking at the position in the x-axis, you're looking at the position in the y-axis. As many masses as the system is made of, and you would divide that by the total mass. So that says m1 y1 plus m2 y2 plus m3 y3, etc., divided by the total mass. So that object, that point in the object, which might be inside the object, it might be outside of the object, doesn't matter what it is, but that point has the special property that it moves according to this equation, very simple equation, which is basically Newton's second law. Three masses, two located on the x-axis. So the idea is to compute the location of the center of mass in the x direction and the location of the center of mass in the y direction. So in the x direction, we proceed according to the definition, right? So we have the mass of the first one, which is m, they're all m, times its position, which is 0 because it's located on the x-axis at the origin, plus the mass of the second one multiplied by its location in the x-axis, which is a, plus, here we have three masses, plus the mass of that guy, which is m, multiplied by its location in the x-axis. In the x-axis, that number 3 is also at a, so that's another a there. And you divide it by the mass, the total mass of the system, which is three masses, you divide it by 3m, right? So that gives you 2/3 of a. So the location in the x-axis of the center of mass will be somewhere here, at 2/3 of this distance. Obviously, it's closer to the two masses, right? To the part of the system that has more mass. In the x direction, you would expect that according to this weight average, right? If you're talking about your GPA and you have a class that have a lot of credits, right? That counts more towards your GPA than a class that only has one credit, right? So your GPA is going to be closer to the class grade that you got for the one that has the biggest number of credits. So the same thing here. These two masses are on the same position in the x-axis, so you would expect that the position of the center of mass in the x-axis to be closer to those two masses than to the one mass, right? So for the y direction, we do a similar calculation. We have the mass, so we're talking about this one, so the mass of that one times its position on the y-axis, which is 0, right? It's lying on the x-axis, so the y position is 0, y equals 0. The second mass is also on the x-axis, so that has a y equals 0. And the third mass is on the, it's at b. so that goes here, divided by the mass of the system, which is 3m. Okay, so when you do that, you get 1/3 of B. So in the y-axis, once again, the center of mass is going to be closer to the these two masses, which are lying on the x-axis, right? So the location of the center of mass is 2/3 in the x and 1/3 in the y. Okay. Then when you have extended objects, say you have a square, a uniform square, uniform meaning that the distribution of mass is uniform, right? The density of the object is uniform. In principle, what you would have to do is integrate, that is, divide the object into small pieces. And since we know how to calculate the center of mass of a small piece, right, it's right in the middle of the little piece, then we will use the definition of the center of mass to calculate the mass. Well, I'll show you an example. But what I want to say here is that when the object is extended, but it is uniform, the density of the object is uniform, then the center of mass is going to be at the geometric center of the object. If the object has symmetries, if it's not some jagged shape that you can't tell where the geometric center is, but if it's something regular like a rectangle, a square, a circle, and so on, the center of mass is going to be at the geometric center of that object, right? So for this rectangle, it will be here. For that square, it will be in the middle. For a circle, it will be in the middle of the circle. So you can use that to calculate the location of the center of mass for a more complicated object, like an object that in this example was made of a rectangle and a sphere or a circle. Okay? So in that case, what you would do is, you know the center of mass of one piece and you know the center of mass of the other piece. Then you apply the definition of center mass, where the mass is concentrated at the center of mass of each piece. So that's what we did here. Said, suppose that the mass of the rod is 1 kilogram, the length is 1 meter, and suppose that the sphere has a radius of 0.1 meters, and the mass of the sphere is 2 kilograms. So how do we calculate the center of mass? I'm going to measure the center of mass from the bottom of the sphere. Calculate the y location of the center of mass. The bar is over here. This is the ball, and the bar is here. So for the bar, the center of mass should be located here in the middle, right? Right in the middle. So that is 0.5 from the top of the circle, right? The location of the center of mass for the circle should be in the center of the circle, or the sphere. So that is 0.1 meters above the bottom, right? And this is going to be my origin, all right? So I'm going to replace the whole bar by a point particle that has a mass of 1 kilogram and is located at the center of mass of that bar. Okay, that would be the strategy when the object is extended. You replace the whole thing with the mass at the center of mass. So what I have now is two masses, 2 point masses, one located here and one located here. So now I can use my definition of center of mass. So the location of that mass with respect measured from here will be what? The location of this mass will be that distance, right? Which is 0.5 and plus 0.2, right? So 0.7 above the bottom level. The location of the center of mass of the ball is right here. So that has a y of, so now I'm going to put that in the equation for the center of mass, which is the mass of the rod, particle number 1, times the location of that particle, yr, the y of the rod, which I just calculated as being 0.7, plus the mass of the ball multiplied by the location of the ball. The mass of the ball is going to be 2 kilograms. The mass of the rod is 1. So I'm going to replace 1 times 0.7 plus 2 times 0.1. And I'm going to divide by 2 plus 1, 3, the total mass of the system. Yeah? 1 times 0.7 plus 2 kilograms times 0.1 divided by 3. And that gives you 0.3 meters. So the center of mass, the location of the center of mass for this system made of a bar and a sphere, is going to be 0.3 meters above the bottom, right? So right over here. Okay, that's where the location of the center of mass is.